6.4, example 5. So now we're going to look at real world situations still, but now this formula is called compound interest. So in an exponential growth, functions are used in real life situations involving compound interest. Although interest earned is expressed as an annual rate, the interest is usually compounded more frequently than once per year. So compounded means that you're adding your amount of interest to your total amount and getting a new total. Then when you compound again, you add the interest to the total and you get a new total. So by compounding, you get new totals that you're earning interest on. So you're really earning interest on interest, and that's compound interest. Here's the formula for compound interest. It looks like this. Y equals P times the quantity of 1 plus R over N to the power of N times T. Let's talk about all of the variables here. Y, again, is still going to be the final amount, what you end up with in the end. The P represents the principal, and the principal is just a fancy word that bank accounts use to represent the initial amount. So it's still the starting amount, the number in front of the parentheses. Then in the parentheses, notice how we still have 1 plus. Because you're earning interest, your money is going up, so you want to add to 1. Now, this is where it gets a little different. Our R is still the rate of growth, and we still want to change it to a decimal. Make sure you change your percent to a decimal here. But our R is being divided by N. N represents the number of times the interest is compounded per year. So let's say that they tell us that interest is compounded quarterly. That would mean it's 4 times per year. If it says semi-annually, then that's 2 times per year. If it says monthly, then that's 12 times per year. So just look out for that key word, and that's going to tell us our number of times it's compounded per year for our N. And our exponent, notice how it's not just T up here, it's N times T. So we're going to use that N again, the number of times it's compounded per year, and multiply it by our T, which is the time in years. Let's look at example 5. You deposit $100 in a savings account that earns 6% annual interest compounded monthly. Write a function that represents the balance after T years. So we're going to start with the formula. The P is the principal. That's the initial amount that we're going to start with. That's $100. Notice we still have 1 plus. Our R is that 6% annual interest. That's 0.06 as a decimal. It's being divided by N, and because it told us we're compounding monthly, that's 12 times per year. So we're dividing by 12. And then this is raised to the power of NT. Again, our N is 12 because it's monthly, but I don't know T in the word problem. It just said to leave T as T. I do want to go one more step and simplify inside of the parentheses here. 1 plus 0.06 divided by 12 is 1.005. And this would be our answer to this question, 100 times 1.005 to the power of 12t, and I would leave my answer just like that. Let's look at another example, and let's let Big Ideas explain.
You deposit $300 in a savings account that earns 3% annual interest compounded monthly. Write a function that represents the balance after t years. First, write the compound interest formula. Y equals P times the quantity 1 plus R divided by N to the N times tth power. Because you deposit $300, the principal P equals 300. Because the account earns 3% annual interest, the annual interest rate R equals 300ths. And because the interest is compounded monthly, N equals 12. Substituting these values into the equation gives Y equals 300 times the quantity 1 plus 300ths divided by 12 to the 12 times tth power, which simplifies to Y equals 300 times 1 and 25/10,000ths to the 12 tth power.